So previously, we talked about how to do a line integral, where basically you have to do every single bit of calculation by hand. And you wind up getting some integral that you have to do, and the integral is set up dt. So let's recall that, and let's also recall that previously we saw the fundamental theorem of calculus for one variable. That's old news for us at this point. So we know that the integral from a to b of f prime of t dt is just f of b minus f of a. So roughly speaking, the integral of the derivative is just the original function, and you plug in the endpoints. So now we're going to combine these two things. We're going to say we have a line integral, but we'd also like a fancy, nice theorem that tells us how to do this in very easy fashion. So for this, we get the fundamental theorem for line integrals. So the fundamental theorem of line integral, which I'm just going to call the FTLI, is actually, it turns out, very similar to the FTC. So the key thing is to understand what is going to take the place of that f prime of t. In other words, what is a derivative which is also a vector? So when do we have a derivative that is also a vector? It's the gradient. So put it together and you get this. And of course, there's different notations there. We could just write f of point B minus f of point A, either way you like. But here we go. It's the integral over the path C of the gradient of function f dot dr equals the original function f evaluated on the endpoints. And now that we know what FTLI is, it's actually possible, it's actually reasonably possible to do a proof of it. Let's take a look. So first, we're going to say that the integral over the curve of the gradient of f dot dr, we're going to write out what that write out what dr is. Another way to write dr is say it's dr dt times dt. And now let's just write out what is the gradient of f and what is dr dt. So gradient of f is, and here I'll write it in 3 coordinates, 3 dimensions. So df dx, df dy, df dz, and then dr dt is dx dt, dy dt, dz dt. So take the dot product and you get this. But we've seen this before. We've seen this when writing out what the chain rule is. So we can just use the chain rule. So by the chain rule, that entire thing in the parentheses is just df dt. So another way to write that is that this is just ddt of f and then integrating that dt. So now we've just got, now we can just use the good old fundamental theorem of calculus from single variable calculus. The integral from a to b of ddt of f of t dt is just f evaluated on the endpoints. Ta-da. Okay. So that's the fundamental theorem of line integrals. That's where it comes from. Here's a nice little proof, but let's get into doing a problem. So let's use it. So let's calculate the integral over the curve of f dot dr, vector field f dot dr, where vector field f is y minus e to the z sine x, comma, e to the z cos x. And c is defined by this path, r equals t, comma, 5t minus t squared, comma, 2t. T goes from 0 to 2 pi. Okay, so remember previously we learned how to do line integrals, as I like to say, from scratch by hand. What we now see is that if our vector field is conservative, boy, this is going to be a heck of a lot quicker. So previously, in a previous example, we figured out that this particular vector field is conservative and its potential function is xy plus e to the z cos x. So knowing that, we can now just calculate this vector line integral directly. So one way to do that is to say, well, I know this is going to be f evaluated on the endpoints, and the endpoints as given on the problem are t goes from 0 to 2 pi. So we want to evaluate f at t equals 0 and f at t equals 2 pi. So in this, one way to do this is that it would help to write f in terms of t. So I take my potential function f, and using the parameterization, let's write it in terms of t. Oops, sorry. And here's the parameterization. So just plug it in. Here's your function f written in terms of t. And so now we know that the integral of, we now know that the vector field f was actually the gradient of f, gradient of function f dot dr. So it's just f of 2 pi minus f of 0. So plug that into the function and you just get this kind of messy expression here. And then you simplify and you just get 20 pi squared minus 8 pi cubed plus e to the 4 pi minus 1. Again, we're just plugging in. And that is how you get to do the problem, and it's that quick. Once you can identify the fact that the vector field is conservative and you have its potential function. So I should mention the last part where we're plugging in the endpoints to the potential function. There's two ways to do it. In this case, we said, let's keep everything in terms of t. Another way to do this is to keep everything in terms of the endpoints vector A and vector B. So another way to do that would be to say the endpoint is at r of 0. And if you plug in 0 for your vector r right here, just plug it in and you get 0, 0, 0. And then another way to do that, and then we would have to plug in 2 pi for t, plug in t equals 2 pi to the formula for r. And that gives us our second endpoint, our A and B, if you like. And then that would give you 2 pi, comma, 10 pi minus 4 pi squared, comma, 4 pi. And then you could plug those in to the original expression for f, not parameterized. So the original expression for the function f, which is right here. Okay. Okay. So let's actually take a look back at what we've just accomplished here. So typically, if you're given a line integral, a vector line integral, what do you have to do? You have to start with your parameterization. Then you've got to plug it in. Then you have to take a dot product. You get some expression in t. You have to simplify it and integrate it, and then plug everything in. What does the fundamental theorem of line integrals tell you? By the fundamental theorem of line integrals, you do not have to do all that work. As long as you know that your vector field f is just the gradient of some function f, then all you have to do is do f of b minus f of a. So that's one thing that the fundamental theorem of line integrals tells you. It tells you something else, which is even more remarkable. Since all you're doing is plugging in the endpoints, notice that the path does not matter, only the endpoints. So it doesn't matter how the path gets from A to B if all you're doing is f of b minus f of a. So this property is called path independence. So mathematically, it's clearly an incredible property. And then when we get to physics applications, there's going to be some extraordinary properties there as well. And then obviously knowing all these things makes calculations a whole lot easier. Doesn't matter how complicated the path is, as long as your vector field is conservative, you're just going to get your potential function and do f of b minus f of a, and then that's the whole story. It's obviously, we obviously want to use this as often as possible, but for that we need to know when do we actually get to use the FTLI. So what we've just shown is that if the vector field is conservative, then we can use the FTLI and the line integral is path independent. So it's also true that if a vector line integral is path independent, then you can conclude that the vector field f is conservative. I have the proof written elsewhere. So let's now go ahead and let's do another problem. So let's calculate this line integral over the curve C of vector f dot dr, where the path C is defined by r equals t comma t squared comma t cubed, with t going from 1 to 2, and there's your vector field. F equals 4x y z cubed, comma 2x squared z cubed, comma 6x squared y z squared. Okay, so once again, normally what would we do? We would figure out the parameterization for C, we already have it. Then we'd make our parameterization for F. Then you make your parameterization for dr, plug that all in, do an integral, blah, blah, blah. But, suspense, okay. This will be much simpler if vector field F is conservative and we have a potential function F. So let's take a look. So one way to check this would be just take the curl of F. So we can confirm that it's conservative as a single step and then find potential function F as a separate step. Here I'm going to sort of do all those things at once. I'm just going to go directly to looking for, does it have a potential function F? If it's not conservative, we would not be able to find a potential function F. And if it is conservative, then we'll find it. So let's take a look. So in the first component, we would say, we hope that df dx equals 4xyz cubed. So integrate with respect to x, and you get 2x squared yz cubed plus some other stuff, which would have to be a function of including only y and z. The second component, we hope, is df dy, and that was 2x squared z cubed. Now integrate that with respect to y to get f equals 2x squared yz cubed plus some other stuff that could only be a function of, that can be a function of x and z only. Third component, df dz, was 6x squared yz squared. Integrate that with respect to z, and we hope, potential function f, which is 2x squared yz cubed, plus some other stuff, which can only be a function of x and y. So can we make all those match up into the same function? Well, in this case, it's really, really simple and straightforward. There's nothing to figure out or match up. The potential function is just 2x squared y z cubed. And typically it would be, we would write plus c, but because this is going to be a definite integral, just like from single variable calculus, we don't need the plus c, we don't worry about it. So to continue, so now we know that our vector field is actually the gradient of a function, so we can rewrite the integral of vector f dot dr is really the integral over c of the gradient of f dot dr. And by the fundamental theorem of line integrals, we know that is just f of b minus f of a. So here I'm going to do it the other way. I'm going to say, what are the actual points? So just to, scroll back for a second. Remember that, yeah, I should do this. Let's get it all at once here. Okay. So since we know that t goes from 1 to 2, and r equals t comma t squared comma t cubed, Then our at t equals 1, plug it in, our point is 1, 1, 1. At t equals 2, plug it in, our point is 2, 4, 8. And so we can just plug those 2 points in for f in its for potential function f in its given form. So plugging in 2, 4, 8, you get 16,384. Plugging in 1, 1, 1, calculate that, and you get 2. So just subtract, and you get 16,382. So let me make a comment about the notation and some other properties. So we just said that well, we're going to take the form that we have for the fundamental theorem line integrals and express it in a different way. So let's recall that from differentials. We know that df equals fx, so just df dx times dx plus df dy times dy plus df dz times dz. But let's actually look at what that form is. That's actually something times something plus something times something plus something times something. That's actually a dot product. So it's the dot product of df dx, df dy, df dz. That's the gradient of f. And then dx, dy, dz, that is just dr. So we can actually write the gradient of f, the gradient of function f dot dr, simply as df from our definition of differentials. So we can now rewrite the fundamental theorem of line integrals using that. So we can write it in this very compact form. The integral over the curve of df is just f of b minus f of a. And 2 comments about this. Number 1, this makes sense because what is actually happening? So on the right side, we've just got the difference in the function values. F of b, f of a, take the difference. So it's like an overall change in f. But what is it that we have on the left side? Well, think of df as a little change in the function values. And what is an integral? An integral is basically an infinite sum. So what's happening on the left side is it says, as you go along the curve, add up all the tiny little changes in the function value. So adding up all the tiny little changes in the function value gives you the total change in the function value, which is on the right side. So conceptually, that's what's actually going on in this formula. Now, of course, what does it take to actually understand this formula? It takes a whole lot of work, and we've done all that work in order to get us to this point. Okay, so now let's find another property of integrals in this case, which we said is a path-independent line integral. So let's say that we've got f, which is a path-independent vector field. And we're gonna, let's see, we're gonna have a path which begins and ends at point A. So that's, but don't look at the calculations on the left, just look at the picture on the right. So this whole loop is called a closed path or a closed loop. So let B just be some other random point on the path. And then we're going to say that you can get to from A to B in 2 different ways. We'll just call them C1 and C2. Okay. So by the definition of path independence, these two vector line integrals are equal. We've said f is path independent, so these 2 integrals have to be equal to each other. So let's manipulate this around and we're going to get a new conclusion. So subtract and you just get one integral minus the other integral equals 0. And now let's remember that C1 goes from A to B, but C2 also goes from A to B, but again on a different path. So instead of subtracting the second integral, we're going to flip the order of we're going to flip the boundaries, which changes the sign of the integral. So now let's remember what this means. This means the integral from a to b, but that was along path C1. And the second one is the integral along from b to a, but that was along C2. So if we go from a to b along C1, and then from b to a along C2, all we've done is we've done the entire path C. So all this means that the integral along the path C of f dot dr equals 0 when C is a closed path, bringing us back to the original point. So we get a new property. So the line integral, the integral around the curve of f dot dr is path independent precisely when the integral along the curve of f dot dr equals 0 for every closed path. So again, it's very important to understand you only get 0 when f is conservative and the path is closed. Okay, let's go back and do another problem. Oh, sorry, just a quick comment. Yeah, we're going to move into applications now. So it's going to be useful to know all this. This comes up a lot because we can use it for any conservative vector field or conservative force, and there are many, many important conservative forces in physics. So we've already talked about maybe the two most important, the gravitational force and the electric force. As we talked about, those are both conservative. So let's take a look. So how much work is done by the gravitational field? And the formula for that, as we said, is F equals GMM over R cubed times position vector R to move a 5 kilogram mass along the triangle from 2, 3 to 4, 3 to negative 6, 1 back to 2, 3. So there's the question. So how much work is done? Well, we know work is a line integral. It's the integral of F dot dr. But what do we know? We know that the vector field F is the gravitational force. It's conservative. And what do we know about our path? We're going from 2, 3 to 4, negative 3, negative 6, 1 back to 2, 3. In other words, this is a closed loop. Therefore, F is conservative and the path is closed. So the work, which is this line integral, equals 0. And now let's bring it back to a more general case. So how much work does the Earth's gravitational field do to bring a 70,000 kilogram satellite from an elevation of 100,000 meters to 40,000 meters? And because we'll need it for the formula, here is the value for the mass of the Earth, because that's the one making the gravitational field. And then also the value for big G, the gravitational constant. So what we need to do is we need to do the work is we know the vector line integral, but we know a vector line integral is much easier when our vector field is conservative. So we've previously shown that the gravitational force field has this potential function, GMM over R. So let's work it all out. So the work is the vector line integral, but we know that the vector field is just the gradient of F. So therefore, we know by the fundamental theorem of line integrals that this is just F of B minus F of A. Now B was we were at 40,000 meters, and then A, the starting place, was at 100,000 meters. So we just have to plug in those values into our potential function F. And then just doing all the calculation, you get this minus this, and it works out to 4.19 times 10 to the 14. And we're calculating work, so this is joules. So again, I want to mainly point out the two big steps. The first big step is recognizing that your vector field F is conservative, so it can be written as the gradient of some function. And then the next big step, in this case, you were given the potential function. If you're not given it, you have to find it. That's a little bit of work. But then the next step, the next key step is the next step here, which is the integral of the gradient of f dot dr is just f of b minus f of a, and that is the fundamental theorem of line integrals. Okay. And I just want to make one comment about this calculation, which is how would a physicist do this calculation? So a physicist would use potential function capital P, and remember that's for physicists, it's negative f. So there's a physics application, so they would write it like this: P equals negative GMM over R, and then your work is the other way around. It'd be P of A minus P of B. So basically it changes some signs around, but at the end of the day, it actually gives you the same value. I just wanted to point out how a physicist would write that down. So the last thing I want to show you is an application from conservation of energy. So let's take everything that we've been talking about, FTLI and all that, and let's apply this to motion. Suppose F is a force field which moves an object. I'm saying any force field, so it could be gravitation, electromagnetism, whatever, just some force field. So in our scenario, we're going to say it's going to move from point A to point B along a path C, which has the formula R of T. And then our starting and ending values for T are little a and little b. Okay. So Newton's second law of motion says that force equals mass times acceleration. So we have F equals ma in scalar form, but we're going to be interested in vector form. So vector F equals m times vector of a. Now further, we know that acceleration is the second derivative of position. So we can write that as force F equals m times r double prime of t. So now that we've written this out in vector form, let's actually try to calculate how much work the force field does to move the object. So let's get into it. So let's apply what we know. We know that work equals, and let's go slow here. So sorry, the equation's all together. Let's just go one step at a time. So first, we know that work equals your vector line integral, the integral over the path of vector of force F dot dr. Now we just said what the force F is. F is m, which is some constant for mass, times r double prime. And we know that another way to write dr is that it's just dr dt times dt, which I'm going to use primes here. So this is just r prime of t dt. Okay. Now, the next step is kind of the tricky step. So how can we rewrite r double prime dot r prime? So one way to do that is to recognize that if you had r prime dot r prime and then take the derivative of that, just use the product rule. By the product rule, that would give you r double prime dot r prime plus r prime dot r double prime. So basically that would give you two of these. So if we want this to be equal, we better put a half in front. So r double prime dot r prime is just half of, or actually the derivative of half of r prime dot r prime. So that was kind of the big fancy step in this calculation. I hope that makes some sense. So let's look at what we've got. So let's reorganize this. So first I'm going to take m as a constant. I'm going to pull it out. 1/2 as a constant. I'm going to pull it out in front. And I'm going to recognize, we know vector identity, r prime dot r prime is just the magnitude of r prime squared. And so then we've still got ddt sitting right there. Okay. So that's how we get this version over here. So now we have to do this integral, but it's just the integral of a derivative of some function. Well, we know what that is by the fundamental theorem of calculus. It is just the original expression. Scroll. It's just the original expression, which is r prime, magnitude of r prime of t squared with the constant m over 2 in front, evaluated on the endpoints. So this is just m over 2 times r prime of t squared from a to b. So plugging in, what does that give? 1/2 m times the magnitude of r prime at b squared minus 1/2 m times the magnitude of r prime at a squared. Okay. So that's the calculation. Now, what does this mean? Let's take a look. So notice that, let's talk about what r prime is. So we know that r is position, and therefore r prime is velocity. But we've got the magnitude of that, and the magnitude of the velocity is just the speed. So what expression do we really have here? This is 1/2 mv squared. The expression 1/2 mv squared you may have seen before in physics. That is called the kinetic energy. So what we just showed is that, and that's called K. So the work done by the field on the object represents the object's change in kinetic energy. So K at the ending point minus K at the beginning point, that's the work. And notice that this is true for any force field. Now, what if the force field is conservative? Then we know that vector field F equals the gradient of some function F. Now, and this is where we're going to go a little physics. The potential, and not the potential function, but the potential energy of an object in a conservative field is defined as P equals negative F. So then we know that, just take the gradient of both sides. Vector field F is just negative the gradient of potential energy P. So we define the total energy to be the kinetic energy plus the potential energy. So E equals K plus P. And for a moment, we're going to assume all other forms of energy are constant, so we get to ignore them. We're just looking at a simplified scenario. So put that all together, and what does that tell us? So, sorry, let's look at it. Let's reanalyze this just in terms of potential energy. So we could say the work is, again, the vector line integral f dot dr, but we know that f is just negative the gradient of p, the potential energy function. And we know from fundamental theorem line integrals that will just be negative p at b minus negative p at a. So once you straighten out the signs, that just gives you p of a minus p of b. So another way to define the work is that it's the change in potential energy, but potential energy at the first point minus potential energy at the second point. So we've expressed the work done in this problem as the field moves the object from point A to point B in two ways. We've expressed it in terms of kinetic energy, and we've also expressed it in terms of potential energy. Let's put those two things together. So we know that they must be equal because the exact same amount of work was done. So we know that the kinetic energy at B minus kinetic energy at A must equal potential energy at A minus potential energy at B. Move stuff around, we get that the kinetic at A plus the potential at A equals the kinetic energy at B plus the potential energy at B. But we just defined that as total energy. Therefore, energy at the point A equals the energy at the point B. Or in other words, the total energy E is constant or conserved. And this is the law of conservation of energy. And it is, here we've only talked about it relative to kinetic and potential energy, but it actually applies to to all total forms of energy. We just restricted looking at 2. And so this is a general principle in physics, and it is also an important example of the reason why gradient fields are called conservative. This is a quantity that gets conserved. Okay, so a big example there. So let's just put up a little summary of all the things that we've talked about for FTLI. So first of all, what is the fundamental theorem of line integrals? It says that the integral, that this particular vector line integral, the integral over the curve of the gradient of some function f dot dr is just f evaluated on the endpoints, f of b minus f of a. First thing. Second thing, all these things are equivalent, which is what we've shown today. So if a vector field is the gradient of some function, that's equivalent to saying that f is conservative. That's equivalent to saying that the vector line integral for f is path independent. Doesn't matter which path you take from a to b. And that is equivalent to saying that the line integral over c of f dot dr is 0 for any c which is a closed path. And we did a bunch of applications for the FTLI, looking at with conservative vector fields, and you can apply them. Many important examples of conservative vector fields like gravitation or electric.